P6.2 Particle Sorting. This photograph is of our very own plush particles, which you'll see in the labs. Okay, well, physicists made particle accelerators and they started smashing particles together at higher and higher energies, and just to see what would happen. So what they found was lots of new particles, and I mean a huge number. In fact, at one point there were more new particles than there were known elements, which was a bit embarrassing. But we're going to focus on a few of them. We've already got protons, which are positively charged, and we've got neutrons, which have no charge, and electrons with a negative charge. And we also now know we have neutrinos, which don't impact on us very much, but we know they're there. In the particle accelerators and also in the upper atmosphere, we found things called muons, which, as we've already said, are like electrons but much heavier. So they've got a negative charge just like electrons have. And all of those particles would sometimes get created in particle accelerators along with their antiparticles. So they're created in pairs, so a proton plus an antiproton, or a neutron plus an antineutron, and so on. But we also got other ones, and the ones you need to know about are pions, sometimes also called pi mesons, and kaons, also called k mesons. Now, both of those come in three types. They can have positive charge, negative charge, or be neutral. And there are many others, but we don't need to know about them at the moment. So, they decided to try and sort the particles out. So we started off with just the basic definition, matter, and that includes, in this context, antimatter as well. And they split it into things called hadrons and things called leptons. So they didn't really know much about them other than they had slightly different properties. So hadrons were particles that were affected by the strong force, i.e. the strong nuclear force. They could also be affected by the electromagnetic force if they were charged. So for example, a proton would be, but a neutron wouldn't. And they could also be affected by the weak force when they decayed, or in the process of decay. Leptons, on the other hand, were not at all affected by the strong force. They were affected by the electromagnetic force if they were charged, so that's just the same as hadrons. And they were also involved in weak force interactions. So there's not much difference between them so far, apart from this business of whether they're affected by the strong force or not. One other difference that might be worth noting is that hadrons could go through a decay process, but although leptons were affected by the weak force, they didn't seem to decay. So let's look at hadrons first. Hadrons were then split into two groups called baryons and mesons. So what's the difference between those? If we start by listing a few baryons. Protons, neutrons, sigmas, and many others are all baryons. And of those, the only one that's actually stable is a proton. So if you're ever asked what a baryon will ultimately decay into, the answer is always a proton. We tend to think of neutrons as being quite stable, and they are when they're in atoms, but on their own they're not. So a single isolated neutron would very rapidly turn into a proton, and so would all the other baryons. Okay, so remember that proton is the only stable baryon on its own. Mesons, on the other hand, don't decay into protons. So that's not terribly satisfactory to define a group of particles by what they don't do, but that's what they had to start with. They don't decay into protons. So baryons do, mesons don't. Okay, now we now know, if you're looking at this before you've done lessons about quarks, this may sound a bit strange, but I think you're more likely to look at this for revision. So we now know that baryons are made of, particles are made of 3 quarks. So all of these, protons, neutrons, sigmas, and there are others, are made of 3 quarks. Mesons, on the other hand, are each a quark-antiquark pair. They're very short-lived, but there's only 2 quarks involved, one of which is an antiparticle, not 3. Okay. Now, the other thing we need to know for now is that energy is conserved in collisions, so in the particle accelerators. So the idea is that the total energy before a collision is equal to the total energy after a collision, an idea you're probably quite familiar with. So in symbols, if we use E0 to represent the rest energy, i.e. the mass of the particles, then sigma E0 means the sum of all the rest energy, i.e. the sum of all the masses, plus the sum of all the kinetic energy of all the particles before the collision must be equal to the sum of all the rest energies plus the sum of all the kinetic energies after the collision. So here's an example from the textbook. On page 21, question 4. It tells you that a K plus meson turns into 3 charged mesons, and on the facing page there's a table listing all of the rest energies of the particles we've just mentioned. So part A asks you to complete this equation. So they're saying a K meson turns into a pi plus meson plus 2 others, because it tells you in the question that it decays into 3. If you look at the rest energies of the particles they tell you about, the pi mesons have a much lower mass than the K mesons, and in fact even 3 of them added together is less than a K plus. So because charge has got to add up to 1 positive, the solution must be that in addition to the pi plus they tell you about, there must be another pi plus and a pi minus. So these two, the charges cancel out and leave you with an overall charge of plus. So that must be the solution to the first part of the question. They then ask you for the kinetic energy of the particles after the collision. So if you look up the rest energy of a K plus meson, it comes to 494 MeV. The rest energy after is the sum of the 3 rest energies of the pi plus and pi minus mesons. So it's 140 plus 140 plus 140, adding up to 420 MeV. So the missing energy must have appeared as kinetic energy. So if you find the difference between those two numbers, 494 is the starting rest energy, 420 is the final rest energy. The difference between them, 74 MeV, must appear as kinetic energy of the particles after the collision.